We're going to be doing an introduction to integrals, and we're going to be answering the question, what is an integral? And even if you've done integrals before and you remember some of the rules, sometimes it's good to be reminded of why you're actually doing it and what it represents. So integrals are often considered to be antiderivatives. So what do I mean by that? I mean, if you have a function, let's say you have a function here, t squared, and you take the derivative of it, you'll have 2t. So the derivative of the function goes that way. But let's say you have 2t and you want to get back to t squared, then you take what we would call, you can call it the antiderivative or the integral. Antiderivative or integral. And up here you have the derivative. So let's say you had, let's say this represented a position. So you had x is equal to t squared. If you take dx over dt, you'll end up over here at 2t. But let's say, and this represents the velocity, but let's say you know your velocity, so your velocity is a known entity, and you want to figure out what the position is when you know the velocity. In that case, you need to take the integral or the derivative. So what's happening when you do this? So if we take the example of a constant velocity, so this demonstrates it the easiest. So let's say we have, consider velocity is constant. So if I were to plot this, I would end up with something that looks like this. We would have time here in seconds, and then up here we have velocity, which is a function of time. And if velocity is not changing, it's literally just a straight line across. And we could even draw that down here. So if we want to figure out the distance, well, distance traveled, distance is equal to velocity times time. And using units, it's easier to see this. So meters is equal to meters per second times time, right? So these would cancel out. And then it becomes very easy to see that the distance traveled is just the area under this curve. Another way to write this out and have the exact same value is to split this into two pieces. Now this would be your delta t, and we'll split it into equal pieces. So this value of time is also delta t. Now, if you want to know the distance traveled, now your distance is equal to the velocity, the same velocity at time t, times delta t, plus your velocity times delta t. So you're just adding up the velocity in the two different blocks. Now, why am I doing this? You're going to see that in 1 second. It's very rare to have a velocity that's completely constant like this. It's much more likely to have a velocity that's changing with time. So let's say you're accelerating away from a stoplight and then you're slowing down to stop at the next stoplight. So let's say you have a velocity curve that looks a little bit more like this. So this is still time in seconds. This is still your velocity as a function of time. But now our velocity is represented by a function that is t times 8 minus t. So this means at time 0 you have no velocity, and at time 8 you have at time 8 seconds it's also equal to 0. Now if we want to find the distance traveled is still the area under this curve. But the problem is that we can't just multiply two values because we don't have rectangles anymore. So what do? Well, what we actually do is I'll take away these marks here. We actually approximate the area using rectangles. And this is why I mentioned splitting the previous one into rectangles, because let's say we approximate this area as the sum of a bunch of rectangles. Now, this approximation is actually pretty close. The only error that we have is represented by these triangles here. So the distance traveled is equal to the summation of v of t, times delta t from I equals 1 to n. N represents the number of rectangles that we have. So the larger the n value means smaller delta t. So n is, the larger n gets, the smaller these rectangles get. And the smaller those rectangles get, the smaller these triangles that represent our error get. And so what we'll do is we'll take the limit as n goes to infinity of our summation of v of t, delta t, oh my goodness, delta t, as I equals 1 to n, so the summation of all of our rectangles. As we approach infinite rectangles, we change our notation, so the summation becomes the integral symbol from A to B, so from two different locations, so from point A to point B, of our equation v of t dt. So now we've gone from having a summation here to actually taking the integral of the velocity equation with respect to time. Notice that we did the same thing as in the derivatives, where our delta t became a dt. But this notation doesn't really help us solve the equation. We still don't know how to figure out what that distance is using this function. So that's what we'll do now. So if we consider that our function was equal to, our distance x was equal to t times 8 minus t, to find the antiderivative, we really just use our reasoning to do reverse derivatives. So I'll expand this so that's equal to 8t minus t squared. So we know that this function is the derivative of something. So what do we know, what function do we know that has a derivative very similar to 8t? And I'm going to write this out as a table. So the antiderivative will go here, and the derivative here. So let's say we have t squared as the antiderivative. The derivative of this will be 2t. And here we have an 8t. So all we have to do is multiply our 2t, multiply it by 4, and we have 8t. We'll multiply this one by 4 as well, so we have 4t squared. So the derivative here is 8t, which is what we wanted, and now we know that the antiderivative is 4t squared. We'll do the same thing for the next term, so we know we need to have a t squared. So using the power rule, we know that over here we're going to have something t cubed. If we take the derivative of t cubed, we have 3t squared. But in our question, we only want to have 1t squared. So we'll just divide this divide by 3, and we get t squared. We'll also divide by 3 on this side, and we get t cubed divided by 3. So now we have the antiderivative for both of our terms. So we know that we're going to have a 4t squared, and we're going to have a t cubed over 3. But we have to add one more term, and that's going to be a constant c, any constant c, because the derivative of any constant is equal to 0. And so it's possible that our antiderivative of our equation has some sort of constant c. So if I rewrite this in proper notation, we have our function x of t is equal to the integral of our velocity function v of t times with respect to time. So now if I plug in the value of this, we have x of t is equal to the integral of 8t minus t squared dt. When we evaluate this integral, this is equal to 4t squared minus t cubed over 3, over 3 plus c. This function here is now our position. So if we input any time t, we can figure out the position of the particle at that point. Now, here, this limit here is considered indefinite because we didn't put any bounds on our integral. So, what do I mean by bounds? Our function looked like this. So if I wanted to know the distance traveled from this point here to this point here, I would say I want to integrate from 0 to 8. So that's saying from time is equal to 0 until time is equal to 8. But I could also integrate from time is equal to 4 to time is equal to 8. And what this will do, if we do from 4 to 8, it's going to take the integral at the upper bound, so it's going to take the integral of this whole area here, and it's going to subtract the integral at this lower bound. So it's going to subtract this integral here. And what we're left with, what we would be left with, is just this piece here. So the integral from 4 to 8 would be just this piece represented in blue. When you do definite integrals, you no longer need to carry the c because they'll cancel out. So I'll rewrite my equation really quick here. So we had x of t is equal to the integral of t times 8 minus t dt is equal to 4t squared minus t cubed over 3 plus c. So in this case, if I want to add bounds to our integral, let's say I do 0 to 4. So I want to know the distance traveled between time equal to 0 and time equal to 4. That means when I evaluate the integral, I add a line here to say I'm evaluating this from time equals 0 to time equals 4. So when I actually plug the numbers in, I write out this equation for 2 moments in time. Once when time equals 4 and once when time equals 0. So now I have x is equal to 4 times 4 squared minus 4 cubed divided by 3 plus c. Again, c is just some random constant, minus 4 times 0 squared minus 0 cubed over 3 plus c. Now you can see here that the c's will cancel out, and they'll always cancel out when you have limits on your integral, so you don't have to worry about them when you have limits. In this case, this whole term actually cancels out here. It all goes to 0. And you only have to evaluate this one term, which means x is equal to 42.67 meters, which is the distance traveled in 4